Thank you very much. And hello, everyone. My name is Gregor Deiss. I'm from the University of Stuttgart. I'm a PhD student there. And today I would like to talk about stellar mergers with HPX, Kokkos, and SYCL. To begin with, let's make it a bit simpler and just talk about HPX and SYCL for a moment. Well, SYCL doesn't need much of an introduction here, but most of you are probably unfamiliar with HPX. So what is HPX? HPX is an asynchronous many-task runtime system, and it's developed at the Louisiana State University in the US. So what does that mean? It's asynchronous in the sense that we build a task graph using futures and continuations. So we have functionality like HPX async here, where we can just take a lambda, run it with HPX async, and get a future back that will become ready once this task has completed. And even if it's not completed yet, we can use that future to chain other tasks to it. For example, here with the continuation then, or if we have more than one dependency, we can also use when or stuff like that. One advantage of HPX is that it's distributed. So this task graph can span multiple compute nodes, as exemplified here. HPX is meant for distributed computing, so it offers quite a lot of functionality for that, like remote function calls, HPX channels to exchange data, and there are multiple communication backends available. And lastly, many tasks. Well, we have a few HPX worker threads. Usually we have one HPX worker thread per CPU core in a thread pool, and they work on millions of lightweight HPX tasks, and those HPX tasks can be suspended. For example, if you launch a GPU kernel and you want the results back to continue with your current tasks, you won't just wait on the GPU result. Instead, you suspend the current task so the worker thread can work on other stuff in the meantime. So that's the idea. So while there is work available within the systems, you never want to have your worker thread work on nothing. And okay, now how do we better yet, why would we want to combine this with SYCL? So I added some small SYCL graph here as well. Why would I want to do that? Well, coming from the HPX side of things, for me, the answer is simple. I actually want to use SYCL in my HPX applications. And if I have a neat integration of the task graphs, it makes me more likely to actually do that. On the other side, of course, if you are a SYCL application developer and you want to distribute your application, you might be happy to have, like, instead of just MPI or Celerity, also another alternative available, for example, HPX now. And another reason is better integration with other libraries. That's also something which I was very interested in. For example, if you have to work with a library that uses SYCL under the hood, for example, Kokkos, which offers a SYCL execution space, having this HPX SYCL integration in turn allows you to better integrate with those libraries as well. Lastly, more efficiency. Well, we can complement the strengths of both HPX and SYCL. So with SYCL, I can write portable compute kernels. I can take care of data dependencies between those kernels. And for HPX, I can distribute my applications. I have those lightweight CPU tasks that I can use for post-processing and avoid any barriers. So it's like the best of two worlds. We can combine it. Okay, let's make the decision. We want to combine it. So how do we go about this? What we want to avoid at all costs is something like this. I hope it's readable, like event wait. So what we want to avoid is having to wait at any point. Instead, what we want is, if we need the SYCL results, then the HPX should know about it and just come back to its current tasks once those results are there. So we want to avoid active waiting everywhere. And of course, the integration isn't much good if the overhead is too large and it gets too slow. So those are the two things. We want to avoid waiting, and we want to keep the overhead as low as possible. And this will basically be the topic of this talk. So you can always see the structure of the talk here in the header line, if I can hit it with the laser pointer. So first, I want to talk about the integration of HPX and SYCL. I will show two alternative ways of implementing that. Then, since I was mentioning overheads, I need a good way to actually measure how good this integration is. So I actually simply skipped ahead and used my, an astrophysics application that I was working on as a benchmark, and see how well the integrations are doing there. And of course, for that, I need to introduce that application in the second section, and afterwards I have results for that as well. But let's start off with the actual integration. So what we have is a SYCL event. We submit stuff, it's running, it's completed. at a certain point. And what we need is right below that, we want just an HPX future that at a certain point goes from not ready to ready. And we want to get that without at a certain point blocking anything on the CPU. Well, the nice thing about this is that's actually already the integration, what we need for it. Because once we have this HPX future that is sort of representing the SYCL event, HPX takes care of the rest because it knows HPX futures. It will automatically trigger any continuations we put to that future. So at this point, we are basically done. So all we need is to convert the SYCL event into a future. And well, how can we do this? Of course, we use callbacks. So one way is basically we have a specialization for future data, which is a part of the future here. And this specialization basically adds a callback during construction that says, okay, if the SYCL event that it's attached to is completed, the callback will be called by whatever mechanism. It will set the future data, and then the future will be ready, and HPX takes care of things. Now, luckily, SYCL is already providing us with just such a callback mechanism, which is host tasks. We can just use a SYCL host task, so why wouldn't we? The nice thing about it is it's basically the easiest way to implement this integration, because all I need to do is, okay, I specialize this future data, and I start a host task, or well, schedule it to the event. And the disadvantage, unfortunately, is this host task is not executed by HPX worker threads. So this might become an issue at the point where you actually run multiple thread pools. So I have my thread pool in HPX, and I don't know what the SYCL runtime is doing. If that has its separate thread pool, this might be a bit of an issue. So how would this look like? Well, to come back to this image just now, we basically now just submit during construction this host task. The host task will eventually be triggered by the completion of the SYCL event, and it will set the data. And implementing that is basically just that. We have the command group that depends on the SYCL event. We have the host task, and the host task is just setting the data. Easy. Now, I mentioned overhead, so I also implemented a second version that doesn't rely on host tasks at all. Instead, what it uses is event polling within the HPX scheduler itself. So what I do is each time I want a future from a SYCL event, I store the SYCL event and a callback in the scheduler itself. When a worker thread needs a new HPX task, it will go to the scheduler. And at that point, it's in there. It can actually quickly poll all available events and see if any of them finished. And at that point, if any finished, it will execute the callback. And in turn, again, setting the future data. Of course, it's a bit more involved, especially with concurrency control, because every worker thread can at any point add these callbacks. And of course, we also don't want to have anything that is really blocking in there. So what happens is only one thread ever polls. Like basically, that can be an arbitrary thread, but while it's in there, the mutex is locked. And while the mutex is locked, the others are just skipping it, because as long as the HPX runtime is alive, it's basically guaranteed that sooner or later another thread will be visiting. So we don't need to wait around at the mutex. You just check if it's in use, if it is in use. Right. And well, the advantages, this way we execute the callbacks with our HPX workers. So that's nice. It works with SYCL implementation that doesn't implement host tasks yet. So that's also nice. The downside, well, someone needs to implement it. So that was more like a personal downside. So I had to work around in the HPX scheduler for that. And the other downside is more of a fundamental issue, because now I have to take into account the overhead it produces with the constant event polling. Like if you have millions of tasks, you at a certain point have quite a lot of events in this scheduler, and at least one worker thread at a time is probably polling it right now. So how bad is it? Which brings me back to, well, I want to actually test it in a proper application. But first of all, I quickly show how this could look like. So basically, we just submit a SYCL kernel like we would normally do. We have our event. And to get our future for that, we just now need to call this getFuture. This will basically create this future, which is a normal HPX future for all intents and purposes, but it uses our future data specialization. So that's the key part here. That's why we need to call this getFuture functionality. But once we have that, we can just use it as like any other HPX feature. For example, just add some continuation that does whatever you want to do on the CPU once this kernel is done. And in case you don't have anything else to do after you submitted that in the current task, you can just suspend the current task until all of that is done. And the worker that was working on it is actually allowed to do other things in the meantime. Since this is a bit inconvenient, I also wanted to be able to use the normal HPX async. So I wrote an executor for that. So now we can basically just call this whole thing with HPX async, pass a SYCL executor, which is just a wrapper around an in-order queue, basically. And now we can submit queue member functions here and pass the parameters. So that's just a convenience layer, basically. You don't need to use it, but you can. Now, coming to the actual benchmark application. So basically, OctoTiger is our benchmark application that we want to use. And it's simulating binary star systems and stellar mergers. So basically, we used it previously to simulate double white dwarf mergers or the contact binary V1309 and other scenarios. The thing is, of course, this takes a lot of compute power, so it's distributed. We previously used it on Cori, Pitstain, Summit, and currently we have our production allocation on Perlmutter, which I believe is currently the top 8 supercomputer, but I might be mistaken. It changes too often. And of course, it's based in the HPX runtime, which brings me to the next point. Why is it a good test for this? Well, I don't have a HPX SYCL application handy because I just now wrote the integration. But what I do have here is an application where all major solvers are implemented with Kokkos. For those of you who don't know Kokkos, it's also a performance portability library, basically. And it offers multiple execution and memory spaces, so you can choose where is my data and where should it be executed with this Kokkos kernel. And notably, it includes a SYCL execution space, which is nice because we can now run this application with SYCL. And we just wrote a HPX SYCL integration, so we can basically use that to get asynchronous kernel launches with Kokkos using the SYCL execution space. And we can turn that on and off, so we can actually judge, is it any good? Does it give us any benefit? So that's why I use this application as a benchmark. And here on the right, you can, by the way, see an example of a current simulation that we are trying where you just have the 2 stars exchanging mass. And you can see on the ISO lines how the velocity on the surface of the stars is currently looking like. Right, so to give you a quick overview of what OctoTiger does, it simulates these stars basically as self-gravitating astrophysical fluids. That means we have a hydro module, which uses finite volumes. We have a gravity module, which uses the fast multiple method. All of that is using adaptive mesh refinement, and we use an octree for that, as exemplified here on the right. This octree uses an entire subgrid of cells per tree node, simply for efficiency. It's a bit of a trade-off between adaptivity and computational efficiency, because I always need to take care of the adaptivity within the kernels otherwise. This way I have a small regular grid with 512 cells at each tree node. And yeah, that brings me to the compute kernels, because this means that during our solvers, we traverse the tree and call the compute kernels per subgrid, basically. So the input for each compute kernel is basically one subgrid and probably its neighbors, because we have ghost cells. Well, this also means that even for small scenarios where we just have like a couple hundred subgrids, as the one I will be using later, we can have thousands of kernel launches within a short period of time. For example, for the scenario I will use later on, we can have around 7,000 kernel launches within 100 milliseconds. So that's actually not uncommon. And well, this also means, since our kernels are not having a lot of work items per kernel, not launching them in parallel or aggregating them together if needed can actually cause starvation on the GPU. So that's an additional difficulty here. Well, and since you were probably wondering how I will plug in this HPX SYCL integration into the Kokkos kernels, there is an integration layer between HPX and Kokkos already. So this one does basically what I want to do. It gives you a HPX future for a Kokkos kernel, but only if there's a get future functionality implemented for that execution space. So that was originally added for CUDA. And now that we have this get future functionality for SYCL as well, I am actually able to use this compatibility layer at all. So all of a sudden this works. So this is great. So now we can basically not just use QDAR HIP as previously, but we can also use SYCL, which is nice. And usually our execution model looks a bit like this. So we have our application here, we launch our kernel, and the kernel, depending on the execution space, either gets run on the GPU, where we instantiate our explicit SIMD types with scalar values, or if we run it on the CPU, there's actually an HPX Kokkos execution space where it gets split into HPX tasks and instantiated with the proper SIMD types, for example, AVX 512 types, using the Kokkos SIMD library. Right. Now, this didn't just fall from the sky. I actually had to integrate all of this. So, of course, I had the HPX SYCL integrations implemented. Now, those are merged within HPX now and will be available in the 1.9 release. I also had to modify HPX Kokkos to basically tell it where the get future functionality is at, and add some optimizations for the deep copy async overload to make it use the SYCL event directly. And a library probably none of you have ever heard of because it's my own. That's just a convenience library for task-based GPU programming, which I use to recycle memory that I need repeatedly for the same task on different subgrids. And it also provides the work aggregation executor that I wrote, which I will use in OctoTiger. But I had to modify it to make the memory pools work with SYCL, so I had to add an allocator for that there. Then, of course, I had to actually tell OctoTiger all of this exists. Please use the correct execution space and memory allocators. And unfortunately, I also had to modify some mask functions because I needed to use the SYCL mask functions when I ran on the SYCL execution space. I'm actually not entirely sure why that was the case, but now the tests pass. So I'm happy with that. And lastly, Kokkos already came with the SYCL execution space. So that wasn't my work, but I looked around a bit in it. And to make it work on the AMD GPUs with this execution space, I had to modify the CMake file slightly to make it work. And I also realized that they have a bunch of internal barriers in the execution space that aren't strictly needed when you use in-order queues. So I got rid of them, and the tests are still passing, so that's nice. Right, but I haven't upstreamed that one yet, simply because I want to test that with something else but OctoTiger for a proper pull request, and I didn't get around to it yet. Right, now let's see. Plenty of time left. Excellent. So let's get to the results. Now I want to reiterate that I want to evaluate the performance with and without the HPX SYCL integration turned on. So basically, I can just turn that off by introducing event wait. Exactly what I didn't want to do, but it's nice enough to actually see if the asynchronicity is actually giving me any advantage or not. I will use a rather simple scenario, actually. So it's just running the Hydro scenario. It's the set of blast wave scenario, which is one of our standard tests within OctoTiger. So it's actually rather nice to test it with that. And even the small scenario, it has like 250,000 cells. And per time step, we run around 7,680 kernels and the associated GPU memory transfers. So all of that is done with Intel DB++, simply because Kokkos within its SYCL execution space is using two extensions, which only they implemented. For example, the submit barrier, I believe, and some other one that I can't remember the name right now. Right. Other than that, we keep it simple for the presentation here and just use the best combination of performance parameters. If you want to see the other runs, they are within the paper, though. And we run it on an NVIDIA A100 and an AMD Instinct 100. Right. So let's take a look at the first integration. So now I just use the host task-based HPX SYCL integration. On the left-hand side, you see the graph on the A100. Right-hand side is the AMD machine. And on the x-axis, I changed the number of HPX worker threads. So basically, at one worker thread, that's a bit stupid. We just use one core with HPX. But what you can see then is how the runtime on the y-axis develops. Because the interesting part here is the speed up I plotted here. That's basically the speed up you get when turning on the HPX SYCL integration. And it's exactly the contention problem I mentioned earlier when I started with the host task integration. Because it works sort of all right for like 1 core, 2 cores. But at a certain point, you just have threads fighting for cores and the performance plummets. So it's not a good integration if your code gets 3 times slower. So that was bad. And on the AMD machine, it's basically the same. It doesn't look quite as bad because the socket actually has more cores to offer, but I ran out of space. So, right. So the overall realization here is the host task-based integration. It was nice to implement because it was simple, but it's actually no good because we want to use as many cores with HPX as possible. Otherwise, it's a bit nonsensical. The event polling integration looks a lot better. So basically here we get a consistent speedup. We can see that here. It's not the largest speedup, but we get that without doing anything else. So that's kind of nice. So we get 11% in the relevant configuration here on the NVIDIA GPU. And we get around 15% here when using HIP, the AMD GPU, and here the NVIDIA. Now I got it correct. And the runtime basically consistently improves no matter what I do. So that was also quite nice. I had not yet had a case where it actually got worse. But keep in mind, those are rather simple tests so far, which actually already brings me to the conclusion slowly. So for the outlook, what I actually want to do in the future is to try some distributed runs with the integration turned on and turned off, because whether the host threads are basically, well, the HPX worker threads are blocked with any waiting should be a lot more interesting there, because they also have to run the communication between the compute nodes. Also, I mean, right now I just ran it on AMD and NVIDIA GPUs, which we already supported, and it would be interesting to run it on Intel GPUs, but the only one I had available was my integrated one in the laptop, so that didn't happen. And other than that, we implemented the integrations. We updated the entire OctaTiger software stack for that. And it turned out the event polling version worked a lot better than the host tasks, at least in the way that they are currently implemented within DPC++. Other than that, the integration is very beneficial. But the software stack also offers a lot of potential for more optimizations, as has been shown with the, Kokkos changes I did, where I could actually remove barriers. And of course, in OctaTiger, there's plenty to do as well to optimize the code. And since I think I have like maybe 1 more minute, this is, for example, on the A100 here on the left-hand side, the runtime per execution space. So since I can now run OctaTiger on the CPU with the old implementation, on the CPU with Kokkos, I can run Kokkos on the CUDA backend, I can run Kokkos on the SYCL backend, and we still have a CUDA implementation. That's sort of what this looks like. And actually, running Kokkos on the SYCL backend gives us a slightly better compute time than running it on the CUDA backend. But both of them are currently still slower than CUDA itself. I took a look at that in the profile. It turns out the kernel runtime is actually quite good here, but we lose out on the API overhead with the polling and the event creation and deletion, actually. So that's annoying, because for CUDA, we have an event pool within HPX, but I couldn't implement that for SYCL because I have no control over the SYCL events. So that was a bit annoying. But yes, this brings me to the conclusion of my talk. And thank you very much for your attention.
Thank you. Thank you. Very good. Got time for 1 or 2 questions?
Yeah.
It's Michael down at the front. Give Alexander a workout.
Thank you. This is amazing work. This is something that I've been wanting to see, is and I want to get your opinion on it, is how to, a direction where we make SYCL much more asynchronous. You know, this is kind of what you're showing, the difference between, you know, having all this asynchronous capability, but doing it correctly, not through the host task, that allows you to get all these benefits. I'm just interested in what you think about that.
So the problem with the host tasks is sort of with HPX, the different thread pools. If you don't have that problem, that you have like different threads competing for the cores, it might actually be a lot more performance. Like, I couldn't test it with OctaTiger, of course, because for better or worse, it's running on HPX thread pools. So, but it might be interesting, because otherwise there's an obvious advantage of running stuff asynchronously, especially if you have small kernels and have to interleave them with, for example, communication, which I haven't even shown here, and it's still beneficial.
Very good. One more, yeah?
In another talk, I asked about coroutines, but now, looking at that, perhaps we should expose a coroutine interface in SYCL Next. So probably we need to talk about that.
Yeah, that would be very interesting. I mean, that's basically what these lightweight HPX tasks are doing if I suspend them. Like in that sense, it's exactly that, what I would need. Yes.
Very good. Well, we'll thank our speaker again. Thank you very much.